Hi BTL Advanced students. Today I will be discussing you all about graphs and Euler circuits. At the end of the discussion, you are expected to define a graph, identifying edges and vertices, determine graphs if they are equivalent, differentiate between Euler circuits and Euler paths, and value the concept of graph and Euler circuits in real-life scenarios. So first class, let's discuss graphs. A graph is a set of points called vertices and line segments or curves called edges that connect the vertices. So here is an example. So these dots class or these points is what we called as the vertices. And these line segments is what we called the edges. So in other example of graphs, it can be curves, but still it can be called as edges. So let's construct a graph. So the following table lists 5 students at a college. So an X indicates that the 2 students participate in the same study group this semester. So look at this X's. So we need to construct a graph that represents this information where each vertex represents a student and an edge connects two vertices if the corresponding students study together. So take note class that the vertices or the points are the number of students and the vertices or the edges, the line segments, are represented by this X, which students or 2 students study together. Okay? So, assuming that we do this graph. So there are 5 vertices to represent the 5 students, Matt, Amber, Oscar, Laura, and Kayla. And connect vertices with edges according to this table. So, si Matt ug si Amber na nag-connect nila, no? So this one. And then Laura and Matt. So si Laura and si Matt na sila ani. Amber and Matt. So si Amber ug si Matt, no? So mao this one. Equal na sila. How about Amber and Oscar? So si Amber ug si Oscar gi-connect na sila. And then Amber and Laura. So connected to the Amber and Laura. So si Oscar connected na siya ni Amber. Then Oscar must be connected with Kayla. So gi-connect sila line segment. And then si Laura is connected with Matt and Amber. Si Laura, Matt, and Amber. And Kayla is connected with Oscar. So as you can notice class that if students study together, they are connected since X represents the line segments. So this will be our graph. Okay. Now class, we have other examples of graphs. So first we have this one. This is a connected graph that has a pair of multiple edges. Okay, what we meant by connected graph is that all the vertices and the edges are connected. And it has a pair of multiple edges. So these 2 vertices here are or connect multiple edges, right? So this vertex connects 3 edges and the other also connects 3 edges. So these 2 vertices are or do connect multiple edges. And the next one, this graph is not connected. It consists of 2 different sections. It also contains a loop. So it is not connected, no, as what we have seen, two sections were different and these are not combined by other line segment here or there, so it is not connected graph, and it also contains a loop. And the third one is a complete graph with 5 vertices, so 1, 2, 3, 4, 5. So a connected graph in which every possible edge is drawn between vertices is called a complete graph. Note, class, that it does not matter whether the edges are drawn straight or curved, and their lengths are not important, nor is the placement of the vertices important. All that matters is which vertices are connected by edges. So consequently, these three graphs shown here are considered equivalent graphs because the edges form the same connections of vertices in each graph. So let's examine this. So we have 5 vertices here, and in vertex B, it is connected with vertex C, vertex D, and vertex E. So it is also the same here. Vertex B is connected with vertex C, vertex D, and vertex E. And also the same process here. Vertex B is connected with vertex C, vertex D, and vertex E. So these graphs are equivalent. So let's have an example determining equivalent graphs. So let's determine whether the following two graphs are equivalent. So, despite the fact that the two graphs have different arrangements of vertices and edges, so as you can see, they are equivalent. So let's examine the edge of each graph. So the first graph has or contains 6 edges. And these are AC, so this is one edge. AE, this is also one edge. BD, then we have BE, CE, and DE, right? So if we do the same for the second graph, we get the same 6 edges, DE, CE, DB, CA, AE, BE, right? So because the two graphs represent the same connections among the vertices, they are equivalent. Okay, now let's move on to Euler circuits. To better understand Euler circuits, we need to establish some terminology. First, we have path. So a path in a graph can be thought of as a movement from one vertex to another by traversing edges. So we can refer to our movement by vertex letters. So for example, in the graph, one path would be A to B to A to C. So that is considered a path. Next, we have closed path or circuit. So if a path ends at the same vertex at which it started, it is considered a closed path, or also called as a circuit. So for this graph, the path A to D to F to G to E to B and to A is a closed path. Why? Since we started with A and we also ended at A. Okay? So we have the path also A to D to F to G to E to H. So this is not a circuit, as the path ends at a different vertex than one it started. So we started at A and we ended at H. So this is not a closed path or circuit. Okay. However, the path A to B to C to E to H to G, then E again to B to D to A rather. So it started with A and also ended at A, but it does not, or it is not, an Euler circuit. So why, class? Since it does not use edges D to F, D to G, and F to G. So in Euler circuit, we must use all the edges, but we can use it once. Okay? Kinahanglan kaisa ta moagi aning edge. So this is an edge. Pero pwede ra moagi balik sa points or sa vertices. So mauna ti i-class. And that is an Euler circuit. So for a graph to have an Euler circuit, it must be first connected, and every vertex in the graph must have an even number of edges sprouting from it. So what do you mean by this even number of edges sprouting from it? So class, as you have noticed, every vertex, if it has multiple edges, nagagikan ana ang vertex. So we have this vertex, and then nag-sprout na siya og multiple edges. So that edges or that number of edges must be even. And what we call this even number of edges, a number of edges that meet the vertex, is called the degree of the vertex. So every vertex must have even degree for it to have an Euler circuit. So an Eulerian graph theorem. A connected graph is Eulerian if and only if every vertex of the graph is of even degree. So that is what we call as the Eulerian graph. Now let's identify this if it is an Eulerian graph. So remember, it must be connected. Then second, it has even degree, or the number of the edges sprouting from every vertex is even. So let's count the number of edges here. So in vertex A, 1, 2. So it is also so it is even. In vertex E, 1, 2, 3, 4. Yes, even. In vertex B, 1, 2, 3, 4. So even also. However, in vertex C, 1, 2, 3. So it has odd number of edges sprouting from vertex C. The same with vertex D. It has 3 edges sprouting from it. So we cannot call this an Eulerian graph since the graph contains vertices C and D where it is of odd degree, right? So by the Eulerian graph theorem, the graph does not have an Euler circuit. So I hope you have followed me, class. Next, we have this graph. So let's examine first the edges. In vertex A, we have 1, 2, okay, even number of edges. In vertex E, 1, 2, even also. The same with D, C, 2, and the same with B. So all vertices are of even degree. So by the Eulerian graph theorem, the graph has an Euler circuit. The Eulerian graph theorem guarantees that when all vertices of a graph have an even degree, an Euler circuit exists, but it does not tell us how to find one. So because the graphs we will examine here are relatively small, so we can rely on trial and error to find Euler circuits. Okay, so let's have this example, finding an Euler circuit. So let's examine this graph. In vertex A, it contains two edges, so even. In vertex B, it contains 1, 2, 3, 4, 5, 6, also even. C, even. D, 1, 2, 3, 4, it is also even. It contains even number of edges. The same with G, E, and F, which contains 4 edges. So, each vertex is of even degree, 2, 4, or 6. So by the Eulerian graph theorem, the graph is Eulerian. And there are many possible Euler circuits in this graph. So, by trial and error method, one Euler circuit is B to A to F, to B again, to E, F, to G, to E, D, to G, to B, to D, to C, and to B. Okay, we started with B and we ended at B also. And take note that we all used the edges once, and that is an Euler circuit. To proceed, class, we have an Euler path. It is a path that uses every edge once and only once. So it is kind of different with Euler circuit, since an Euler path does not require that we start and stop at the same vertex. So it requires that we need to use every edge once and only once. Okay? An Euler path theorem, a connected graph contains an Euler path if and only if the graph has two vertices of odd degree, with all other vertices of even degree. Furthermore, every Euler path must start at one of the vertices of odd degree and end at the other. So to clearly explain Euler path theorem, class, in Euler path, the degree of the start vertex must be odd. So we need to start with a point that sprouts odd number of edges. Okay. Then the ending vertex must also be of odd degree. The same with how we started, and we ended it with odd degree. Okay. The end must be a vertex which sprouts odd number of edges. Then all other vertices, just as in the case of an Euler circuit, must be of even degree. So in Euler path theorem, class, duha ra ang odd, ang start ug ang end. However, ang other nga mga vertices, even degree na sila. Okay? Okay, class, we have this application of an Euler path. A photographer would like to travel across all of the roads shown on the map. The photographer will rent a car that need not be returned to the same city, so the trip can begin in any city. So the question is it possible for the photographer to design a trip that traverses all of the roads exactly once? So okay, looking at the map of roads as a graph, we see that a road that includes all of the roads but does not cover any road twice corresponds to an Euler path of the graph. Notice that only two vertices are of odd degree, the Alameda, 1, 2, 3. So it is odd. And the other one is Dover. The city of Dover, 1, 2, 3. And the rest, it contains 2 or 4. Thus, we know that an Euler path exists, right? So it is possible for the photographer to plan a road that travels each road once. Because Alameda and Dover are vertices of odd degree, the photographer must start at one of these cities. So with a little experimentation, we find that one Euler path started with the city of Alameda, to Burleigh, to Caldwell, to Dover, to Burleigh again, Fairmont, then Alameda, Grangeville, to Fairmont, to Evanston, and to Dover. So class, it starts with the city of Alameda and ends at Dover, which are of odd degree. So that ends our discussion for today, class. If you have queries regarding the lesson, you can chat me directly. Okay? For your assessment, here it is. I will post this in our Google Classroom as well as the assignment. Thank you, class, and happy learning.